Hello and welcome to ResearchPod. Thank you for listening and joining us today. In this episode, we will be looking at the research of Rebecca Mathews, a food regulatory consultant and scientific writer. She examines whether the soluble fibre beta-glucan found in oats and barley has an impact on weight management. Obesity is an ongoing public health concern. The combination of abundant high-calorie foods with a lack of physical activity has gradually expanded our waistlines. The increased prevalence also leads to a rise in obesity-related illnesses, such as type 2 diabetes and cardiovascular disease, and certain cancers are also on the rise. Engaging in more physical activity and replacing high-calorie, low-nutrient foods with healthy whole foods is the simplest weight loss strategy. Recent evidence has suggested that whole grains and dietary fibre impact weight, with many observational studies suggesting a link between cereal fibre, whole grain and lower body mass index, or BMI. This link was clearly evident in meta-analyses of randomised controlled studies in which subjects did not change their usual diet. Here, isolated soluble fibre or viscous fibre in whole foods was shown to reduce body weight and BMI. Soluble or viscous fibre was also shown to induce an even more significant reduction in body weight when combined with a calorie-restricted diet. The effect of individual fibres was not assessed in these meta-analyses, but soluble fibre as a whole, which included psyllium, guar gum, konjac and beta-glucan, demonstrated a beneficial effect. Beta-glucan is an indigestible carbohydrate or dietary fibre concentrated in the bran layer, which is the hard outer layer of oat and barley kernels. Rebecca Mathews and her collaborators wanted to determine if there was reliable, consistent evidence supporting a relationship between beta-glucan, weight loss and body fat, and whether there were plausible physiological mechanisms that would explain the effect. Oats and barley are the richest sources of beta-glucan, and both are whole grain foods that can readily be incorporated into the diet. Other cereal grains, such as wheat, rice and corn, do not contain beta-glucan. In 2009, the European Food Safety Authority offered their scientific opinion on the ability of beta-glucan to maintain or achieve normal body weight based on a health claim petition submitted to them. The agency concluded that a cause and effect relationship could not be established based on the evidence provided. Although a few studies reported on the effect of beta-glucan on satiety, none of the studies specifically addressed the impact of beta-glucan on body weight. Another review summarizing clinical studies on beta-glucan showed a correlation between reduced body weight and BMI, but found no impact on the circumference of the study subject's waistline. Furthermore, this review did not consider every study that evaluated the effect of beta-glucan on body weight, nor did they assess the quality of the studies. Due to these uncertainties, Mathews and colleagues aimed to conduct a more comprehensive overview of beta-glucan, body weight, and adipose tissue. The aim was to examine the totality and quality of the evidence in a process similar to what regulatory agencies, such as the US Food and Drug Administration, and the European Food Safety Authority use to verify health claims. Multiple searches were conducted using large scientific databases of peer-reviewed papers published in English across the globe to identify all human observational and clinical studies that evaluated the effect of beta-glucan on body weight or body fat parameters. A total of 4 observational studies and 72 intervention studies were identified. Even though body weight changes were measured in these studies, the majority were not specifically designed to examine the role of beta-glucan on body weight. Most were designed to study the effects of beta-glucan on lowering blood cholesterol or blood glucose levels, and participants were told to maintain their body weight for the duration of the study. Since inclusion of these types of studies would significantly bias the evidence, they were excluded from the review. All remaining studies were evaluated for quality. Several factors were considered when assessing the quality of a study, such as if they were randomized, double-blind, controlled for bias, used a calorie-matched placebo food in place of the beta-glucan-containing food, had an appropriate sample size with a low dropout rate, and good compliance to the study protocol. Studies that did not meet these criteria were considered low quality and excluded from the analysis. Data collected between 2001 and 2010 from about 14,700 children and 22,800 adults by the National Health and Nutrition Examination Survey in the US showed that those who consume cooked oatmeal had a lower risk of being overweight after adjusting for potential confounders such as gender, age, race, ethnicity, physical activity, poverty-income ratio, and smoking status. Another observational study of 713 school children aged 8 to 11 years, conducted in Denmark, reported that the higher the intake of whole grain oats, the lower the fat mass measured after adjustment of confounders. A fourth data evaluation by the National Health and Nutrition Examination Survey of children and adults between 2009 and 2012 also revealed that underweight, normal weight and overweight individuals ate more cooked oatmeal than obese individuals. However, this last study was not given much weight because the analysis did not consider potential confounders that could have biased the outcome. Observational studies tell us whether there is a potential relationship between a food ingredient and a specific health effect. While the 3 observational studies suggest an association between oat intake and body weight and body fat, cause and effect cannot be established. Well-designed, randomized, controlled clinical studies that investigate changes in body weight and body fat after subjects consume foods containing beta-glucan compared to a placebo allow the determination of a true causal effect. After low-quality studies were eliminated, conclusions were drawn from 6 high or moderate quality studies that were conducted in adult overweight subjects living in Japan, Taiwan, Brazil, Venezuela, and the United States. About 75 to 80% of the studies that measured body weight, BMI, or body fat-related measures observed a significant reduction when subjects were consuming their usual diet or healthy diets. However, only 33% of the studies that measured waist circumference reported a decrease. The beta-glucan dose that was consumed ranged from 3 to 7 grams a day for 6 to 12 weeks. Oats and barley as sources of beta-glucan can be consumed in a variety of foods. Around 1.5 cups of cooked oatmeal provides 3 grams of beta-glucan and 1 cup of pearled barley provides 2.5 grams of beta-glucan. Several potential mechanisms underlying the effect of beta-glucan on weight loss have been proposed. One possibility is its effect on satiety, or the feeling of fullness, which inhibits further eating. When subjects were asked to rate their feelings of satiety after consuming beta-glucan foods, some studies did not see an effect, but several did. Another mode of action could be delayed gastric emptying caused by beta-glucan's ability to absorb water and form a viscous mass. One study from 2015 found that cornflakes passed through the digestive tract faster than an energy-equivalent amount of oatmeal. This was attributed to the fibre content, as the cornflakes had no dietary fibre. In addition to dietary fibre, the molecular weight of beta-glucan was found to be a significant factor in delaying gastric emptying, with higher molecular weight unprocessed beta-glucan passing through the gastrointestinal tract at a much slower rate than lower molecular weight beta-glucan. Processing can affect the molecular weight of beta-glucan. In another study, test subjects were given a high-viscosity oat bran beverage and a low-viscosity oat bran beverage. The researchers were surprised to find that participants drinking the low-viscosity oat bran beverage reported feeling significantly more satiated 3 hours later. However, when they measured the energy intake of participants for the rest of the day, the total energy intake of those who consumed the high-viscosity drink was significantly lower than those who consumed the low-viscosity drink, suggesting that the effects of viscosity on appetite and energy intake may only be evident later in the day. Viscous fibres have been shown to delay the intestinal absorption of nutrients, which stimulates the production of appetite-regulating gut hormones. When 3 grams of extracted barley beta-glucan was consumed in a drink at breakfast, the appetite-stimulating hormone ghrelin was decreased and pancreatic polypeptide, a hormone that reduces appetite, was significantly increased. Additionally, it was observed that eating increasing amounts of beta-glucan was associated with rising concentrations of plasma peptide YY, a hormone known to reduce intestinal motility and food intake. The influence of beta-glucan on gut microbiota is a developing area of study and another potential mechanism through which beta-glucan may impact body weight and body fat. Previous research has shown that transplanting the gut microbiome from obese mice into lean mice caused the lean mice to develop a higher fat mass. This suggests that gut microbiota play an important role in energy regulation. Although there are studies that show beta-glucan consumption enhances the growth of specific gut bacteria, very few have examined the possible association with body weight or body fat. In one study, beta-glucan increased bacteroidetes and decreased firmicutes, and this shift was correlated with a lowered BMI and waist circumference. On the other hand, changes in bifidobacteria and Akkermansia were not significantly impacted, whereas another study reported an increase in bifidobacteria after the consumption of oat beta-glucan. The risk of obesity has been linked to a decrease in bifidobacteria and Akkermansia. Several factors, such as the subject's original microbiome, usual diet and dietary fibre intake, and the dosage of beta-glucan, would impact which gut bacterial species are enhanced by beta-glucan. In addition to its potential impact on microflora communities, beta-glucan has been shown to have a profound effect on short-chain fatty acids. These are produced when gut bacteria digest dietary fibre such as beta-glucan and serve as an energy source for colon cells. Short-chain fatty acids have been shown to have direct effects on fat cells and thereby regulate metabolism by participating in the body's appetite and energy management signals, such as hormone expression. A study with mice demonstrated decreased gene expression involved in fat metabolism in liver and fat tissue, and a correlation with increased short-chain fatty acids following the intake of beta-glucan. More research is needed to confirm the potential anti-obesity effect that may be induced through changes in gut microbiota and short-chain fatty acid production following the consumption of beta-glucan. Overall, the totality of the observational and clinical evidence suggests that oat and barley beta-glucan-containing foods may aid in preventing weight gain and adiposity, and there are multiple plausible mechanisms that underlie this effect. Additional studies are required to further the understanding of this phenomenon. That's all for this episode. Thank you for listening, and stay subscribed to ResearchPod for more of the latest science. See you again soon.